In this section, we're going to start taking a look at some of the techniques of being able to evaluate integrals that are not on that basic list. And one of the most common techniques for non-basic integrals is by integrated by something called a U substitution. Okay. Now, U substitution is essentially going to be the reverse of the chain rule from the chain rule from your derivatives. Essentially, what you're going to be doing is letting U be equal to a composite part of the function, and then taking the derivative of that and hoping that it gets the rest of what's outside of that function. So U substitution is one of many topics in Calculus 2 that we're going to be studying for techniques of integration. So a few of those are going to be U substitution, which we're going to cover in this lesson series. But then all throughout the next series, we're going to be looking at techniques like integration by parts, trigonometric integrals and trig substitutions, partial fractions, and improper integrals. So let's focus today on being able to work with the U substitution. U substitution means that if you have a function or an integrand of this form, where you have an interior function with a composite, and you could take its derivative and it equals what's on the outside, you can rewrite that function as f of u, and hopefully that's something that you can integrate. Okay. Now, sometimes you have to go through and you have to massage the function a little bit algebraically before you can do that. All right. So in this chapter or this section, we're going to learn all those different techniques. Some ways to define U, or some techniques. Let it be what's in parentheses. So U equal in parentheses. All right. You can also make U be equal to what's in the denominator as well. Right? So in paren, in a denominator, okay, under a radical. All right. These are usually the common ways to do a U substitution, but it's not all of them. All right. So as we're going to see later in the course, there's lots of different ways to define U throughout. All right. But these are just some of the common ones that we can start with. Now, what we're going to do is we're going to do several examples of being able to evaluate both definite and indefinite integrals that require a U substitution. All right. So let's start off with a really basic example, sine of 2x. Now, we could probably just think of a function to where we could take its derivative and get the sine of 2x. And that probably would be negative 1/2 cos of 2x. So, but truly, this is a U substitution problem, right? So here's what we're going to do. We're going to let U be equal to the interior function, which is 2x. We still need to substitute for dx, okay? So we're going to find a derivative, and du is going to be equal to 2. The derivative of x is 1. And so we're going to be left with 2 dx. Now, that's almost good, except for this 2 right here. So what I'm going to do is I'm going to divide both sides by 2, and we end up with the other part of the substitution being du divided by 2 is going to be equal to dx. So wherever we see dx, we're going to substitute du over 2. And wherever we see a 2x, we're going to plug in a u. So this integral now becomes the integral of sine of u. So instead of 2x, now we're making this in terms of u. And then also, instead of the dx, we're going to plug in du divided by 2. Now we can factor out a half. And so we're going to end up with 1/2 of the integral of sine u du. And we know that the antiderivative of sine u, or the integral of sine u, is going to be a negative cosine of u. All right, so this is going to wind up being 1/2 negative cos of u plus a constant of integration c. And the last step that we're going to do with this, we're going to back substitute in terms of x. Okay, so last thing we're going to do is we're going to make this negative 1/2 cos of 2x plus c. And that's going to be our antiderivative. All right, so go back through the steps again. Okay, first step, choose a u. All right, most of the time it's going to be some interior function, and then find the derivative as well. And hopefully it gets either close or exactly to what's remaining outside of that function. Then you integrate. Okay, so step 2, you're going to integrate. And then the last step is to back substitute in terms of the original variable. Let's take a look at a couple more examples. Another example is e to the 5x. No parentheses here, okay, but there is a composite function, which is 5x, right? So we know that e to the x could be written as e to the 5x, or if x were to be substituted with 5x as an interior function g of x. The derivative of 5x is going to be 5, and then dx, because it's with respect to x. We like the dx, but we don't like the 5. So what we're going to do is we're going to divide by 5, and we're going to wind up with du fifths is equal to dx. Wherever we see dx, we're going to substitute du fifths. Wherever we see 5x, we're going to substitute u. And so this now becomes the integral of e to the u du fifths. Or we could factor out the 1/5 and write this as integral of e to the u du. We know that the antiderivative of e to the u is e to the u. So this becomes 1/5 e to the u plus c. And then finally, we back substitute for u, 1/5 e to the 5x plus c. Now, one of the tricks that we're going to see throughout the semester is that if you have a function that you know the antiderivative of, like sine or e or cosine, and you have an interior function that's like a 2x or 5x or pi x, then what you do is you just take the derivative or the antiderivative of the larger function, which in this case would be sine, and then you divide by whatever that interior function's derivative is. All right, so eventually we're going to see that shortcut, but I'm just illustrating that to be able to do that, you need a u substitution. One last example before we finish up this video and go on to more examples in the next video. We have 3x squared, square root of x cubed minus pi plus 753 dx. Looks like a really nasty one, okay, but it's not that bad. Let's let u be what's under the radical. Okay, so again, try to let u be equal to some sort of interior composite function. So this is going to be x cubed minus pi plus 753. And the good news is when you take the derivative of this, the derivative of x cubed, 3x squared, the derivative of pi, 0, the derivative of 753, 0. And that gives us precisely what's on the outside of that function. So wherever we see 3x squared dx, that's going to be our du. And then under the radical is just going to be a u. So in terms of u, this integral now becomes the square root of u. So I replaced x cubed minus pi plus 753 with u. And then instead of dx 3x squared, that just becomes du. To evaluate this, we're going to rewrite this as u to the 1/2. Now we're going to add 1, divide by the new exponent, antiderivative. So u to the 3/2 over 3/2 plus our constant. We're going to back substitute for u and clean this up. So one possible answer could be 2/3 multiplied by the reciprocal of the denominator, square root of u, so we're going to substitute or back substitute for u, which was x cubed minus pi plus 753, and it was cubed plus that constant of integration c. Okay. If you wanted to leave it as 2/3 quantity x cubed minus pi plus 753 to the 2 or to the 3/2 power, that would be acceptable as well. Okay, so that could be another possible answer out this. Okay, so these are some of the rudiments of use substitution. Okay, so we're going to take a look at more of these examples in subsequent videos, but it might be helpful for you to go back through and make sure that you can evaluate these three, because these three are really simplistic. As we go along, we're going to get into more detailed and more complex examples.